EEE EC 201 Electrical Circuits 1. In today's lecture, we will study a technique of circuit analysis known as nodal analysis. We will study the application of node analysis in electrical circuits having both independent and dependent sources. At first, we will study how to apply node analysis in electric circuits having independent current sources. In order to apply this technique, there are certain steps which we need to follow. Number 1. At first, we need to determine the number of nodes within the network. Number 2. We need to identify a reference node, which is usually the ground or zero voltage level, and then the remaining nodes must be labeled with a distinct voltage. Number 3. We need to apply KCL, that is Kirchhoff's current law, to each of the nodes except the reference node. Number 4. We need to solve the resulting linear equations in order to determine the assigned nodal voltages. If we consider the circuit given over here, this network has two nodes. Node 1 is this one. These points, if we refer this as A point, this as B point, and this as C point, then all these 3 points are connected together. There is no element between point A and point B, and there is no element between point B and point C. Hence, all these 3 points will have the same voltage, and thus they are referred as one node. Over here, the other node is the ground or the zero potential level. The point D, point E, and point F all are connected together to the ground. So, this is the reference node and this is the other remaining node with a voltage marked as V1. Example 1. Calculate the node voltages in the circuit shown below. Step 1. We need to identify the nodes for this particular network. So, this is the reference node, which is the zero potential or the ground. This point is node 1 and this point is node 2. The next step is to apply a voltage to each of these nodes. Considering this point as node 1, we can assign the voltage V1 over here, and considering these points as node 2, we can assign the voltage V2 over here. The next step is to apply KCL or Kirchhoff's current law to each of these nodes except the reference node. Now, if you remember, KCL states that sum of the currents entering a node must be equal to sum of the currents leaving the node. So, if we assume that I1 is the current entering the node, then I1 must be equal to I2 plus I3. Hence, we have written down the expression I1 equals I2 plus I3. Now, if we substitute the actual current values in this expression, we will get, if you observe here, 5 ampere based on the direction and magnitude of the source, current source, 5 ampere is the current flowing through this branch. That is, 5 ampere is the current flowing through this entire branch. Thus, I1 is equals to 5. Hence, we have written 5 over here. I2 is the current which is flowing through the 4 ohm resistor. Now, we know the voltage at this point is V1 and the voltage at this point is V2. So we can easily determine the voltage drop or potential drop across the 4 ohm resistor, which is basically V1 minus V2. Now, using Ohm's law, we can determine the current I2, which is equal to V1 minus V2 divided by 4. Hence, we have substituted the value over here. I3 is the current flowing through the 2 ohm resistor. Over this point, the voltage is V1, and over this point, the voltage is 0 volt. Therefore, the drop across the 2 ohm resistor is basically V1 minus 0. Now, again applying Ohm's law, we can determine the current I3 which is flowing through this resistor. And that is equal to V1 minus 0 divided by 2. Rearranging this expression, the final linear equation which we will get is 3V1 minus V2 equals to 20. By using the same procedure across node 2, we can determine the second linear equation. We know that at node 2, the voltage is V2. I1 is the current which will be leaving this node. I4 is the current which will be entering this node. I2 is the current which will be entering this node, and I5 is the current which will leave this node. Hence, I2 plus I4 is equal to I5 plus I1. Thus, we wrote this expression. Again, if we substitute the actual values in this expression, we will get I2 equals V1 minus V2 divided by 4, and I4 is equal to 10 ampere. Thus, V1 minus V2 divided by 4 plus 10 ampere equals 5 ampere, which is the current leaving through this branch, and I5, which is equals to V2 minus 0 divided by 6. Rearranging this equation, we'll get the second linear equation, which is minus 3V1 plus 5V2 equals to 60. On solving these two linear equations, we can easily determine the values of V1 and V2, which in this case will be equal to V1 13.33 volts and V2 20 volts. Example 2. In this example, we will study another convention which can be used to write down the equations when we apply KCL across a node. There is no hard written rule that you have to follow this specific convention. You can follow either convention, whichever you find easy. Different textbooks uses different convention to achieve those equations. Hence, we are just making you familiar with all the conventions. In this convention, which we will use for this example, when we apply KCL across a node, we assume that the voltage across that node is at higher level than the voltage of the other nodes. For example, when we apply KCL across node 1, we will assume that V1 is at higher potential than V2. But when we will write down the equations, or when we will apply KCL across node 2, we will assume that V2 is at higher potential than V1. So, in this example, you have been asked to apply nodal analysis to the network below. This network has 3 nodes. The ground or the reference node. These 3 points form node 1 and these 3 points form node 2. V1 is the assigned voltage for node 1 and V2 is the assigned voltage for node 2. So, Based on the direction of the currents as shown over here, when we apply KCL across node 1, the equation which we'll get is I1 plus I2 plus I will be equal to 0. Now, I1 is the current flowing through R1. The voltage across this terminal of R1 is V1 and the voltage across this terminal of R1 is E. Since V1 is at higher potential than E, thus the current flowing through R1 will be equal to V1 minus E divided by R1. I2 is the current flowing through R2. The voltage across this terminal of R2 is V1 and the voltage across this terminal of R2 is V2. So the potential drop across R2 is V1 minus V2. Hence, the current flowing through R2 will be equal to V1 minus V2 divided by 4, which is shown over here. I is the current which is indicated by the independent current source. Hence, if we substitute the values of I1, I2 and I in this equation, this is the equation which we will get. Now, as I have mentioned earlier that for this particular example, when we consider a particular node, we will assume that the voltage or potential at that point or at that node is at higher level than all the other nodes. So, when we apply KCL at node 2, we will assume that V2 is at higher potential than V1. Hence, the direction of this current will change. Now, we will assume that I2 is the current flowing from V2 towards V1. So, if that is true, then after applying KCL, the equation which we will get or the expression which we will get is I equals I2 plus I3. I3 is the current flowing through R3. The voltage across this terminal of R3 is V2 and the voltage across this terminal of R3 is 0. So, the potential drop across R3 will be equal to V2 minus 0, which is basically V2. And the current I3 flowing through R3 will be V2 by R3. Again, if we substitute the values of I, I2 and I3 in the expression over here, this is the equation which we will get. Solving the two linear equations, we can easily determine the values of V1 and V2. In this case, V1 will be equal to 37.82 volts and V2 will be equal to 32.73 volts. Since we know the values of V1 and V2, we can easily determine the currents flowing through the network. In this case, IR1, the current flowing through resistor 1 will be 3.27 ampere, I3 will be equal to 3.27 ampere and IR2 will be equal to 1.27 ampere.